Hello friends, and welcome to another space journey. Let your shoulders settle, your jaw unclench, and your breathing find an easy rhythm. You don't need to keep up with anything tonight. The sky moves on its own. But before we drift, let a few soft questions float up. How does the moon glow when it makes no light of its own? Where does night surrender to morning with such careful timing? What first lit the sun, and why do the planets never slip away? Are there other worlds with seas hidden under ice, or skies the color of copper rain? If you could hold a grain of starlight, would it remember the moment everything began? Our neighborhood in space formed about 4.6 billion years ago, from a collapsing cloud of gas and dust, and its center became the sun, a steady engine that keeps everything else in orbit. Almost all of the solar system's mass is gathered there, more than 99%, so the paths of planets and small bodies trace curves around that brightness without argument. Light from the sun takes just over 8 minutes to reach Earth, crossing the space between in one quiet line. By the time you notice its warmth on your face in daytime, those photons have already traveled far and finished their journey. The planets follow elongated loops rather than perfect circles, and each path brings a nearest point and a farthest point from the sunday. Motion quickens near the close approach and eases near the far end, a rhythm described centuries ago and confirmed ever since. Some worlds hold thick atmospheres, some only thin veils, and some carry magnetic fields that redirect charged particles away from their surfaces. Others, with weaker defenses, have watched gases drift into space grain by grain across deep time. Within this system, moons travel with their planets, some round and large, like miniature worlds, others small and irregular like captured stones. Earth's companion is unusually big compared to its planet, and steadies the tilt that gives us seasons. On more distant orbits, the giant planets gather swarms of satellites, and some of those icy companions likely hide liquid water beneath crusts. Closer in, heat can be severe, and air can become chemistry in motion across the whole span. Faint debris and leftover building blocks continue to circle in belts and scattered populations. Every piece keeps its own appointment with gravity. As you listen, let the details settle at their own pace. If your eyelids grow heavy, that is welcome. Curiosity can remain soft and unhurried. Nothing in the night sky demands effort. It only invites attention. If these gentle travels bring you ease, feel free to rest where you are. We'll wander through nearby facts one by one, steady and unforced, letting each idea arrive and fade. Think of the solar system as a quiet town with wide streets and predictable clocks, and allow yourself to stroll without destination. When you're ready, we'll begin. Before anything else, the star at the center sets the rhythm. Its visible surface, the photosphere, glows at about 5,500 degrees Celsius, while the outer atmosphere above it, the corona, reaches temperatures that climb into the millions. That surprising inversion is a signal. Energy is being moved upward by magnetic waves and countless small releases that heat the rarefied plasma aloft. Deeper down, in a central region under crushing pressure and staggering heat, nuclei of hydrogen fuse into helium and free energy that begins a very slow journey outward. Photons scatter and zigzag through dense layers for ages, before finally emerging as the light that washes every world. From there, the path is simple. Light travels straight until something meets it, and warmth is carried across the family of orbits like a steady heartbeat. The star's face is never truly still. Darker regions, called sunspots, appear where strong magnetic fields suppress local convection and lower the temperature compared with their surroundings. Their number and complexity wax and wane, in a cycle that runs roughly 11 years, a pulse that makes the surface sometimes busy with active regions and sometimes relatively plain. Those fields can twist until they snap and reconnect, releasing flares that flood space with radiation, or launching great clouds of magnetized particles that sweep past planets days later. When such gusts reach Earth, they compress our magnetic shield and feed shimmering auroras near the poles. Even during quieter periods, subtle oscillations ripple across the photosphere. Helioseismology reads those waves to map flows hidden beneath the light, revealing how plasma circulates and how rotation changes with depth, a portrait of a living interior drawn from surface tremors no ear can hear. Beyond the light, the star breathes, a constant outflow of charged particles. The solar wind escapes along open magnetic field lines. That wind inflates a vast bubble, heliosphere, that envelopes the orbits and stretches far beyond the outermost planets. Inside the bubble, field lines spiral with rotation. Comet tails lean away from the star even as their heads move along their own paths, and tiny dust grains feel a pressure that gently herds or disperses them. The wind is thin, yet over distance and time it is decisive, a constant breath that gives the system its magnetic weather. Power is balanced by loss. In the core, matter transforms into energy. At the surface and in the wind, mass trickles away. Over a human lifetime, the star's weight changes by a fraction too small to feel. Yet, over geologic expanses, the effect accumulates. For now, the output remains stable enough to keep liquid water possible on one world and to warm others in measures suited to their distance and dress. The light that reaches us is steady on the scale that matters most for daily life. Tiny fluctuations ride on top, tied to spots and fields, but the long arc is calm. That steadiness is why calendars can be traced across centuries, and why seasons return on schedule. Think of the star as a slow, dependable metronome whose ticks are heat and light, keeping time for every orbiting companion. Even the apparent face carries texture that speaks of deeper structure. Granules, cells of rising hot plasma, and sinking cool plasma freckle the photosphere, each lasting minutes, each wider than countries. At larger scales, supergranules sweep materials sideways and braid magnetic fields into networks. Towering arches of gas follow loops of magnetism and sometimes erupt in great prominences that rise from the limb and fall back gracefully. Bright faculae gleam near the edges of the disk, subtle hints of fields and heat flow. The star rotates differentially, faster near the equator than the poles. That uneven spin stretches and winds field lines until they snap, a winding and unwinding that underlies the cycle of spots and flares. What looks like a clean circle through a simple filter is, in detail, a layered, changing surface where motion, heat, and magnetism intertwine. Radiation comes in more colors than our eyes can see. Ultraviolet light from higher layers bathes planetary atmospheres and drives chemistry, carving and charging the thin upper regions where satellites fly. X-rays brighten during active times, tracing the hottest loops in the corona. In the deepest sense, even particles born in the core neutrinos pass through the star and through matter beyond, with barely a touch, swift witnesses that fusion is ongoing now, not just inferred from surface light that began its journey ages ago. Each band and particle tells a part of the same story. Energy that starts in fusion, moves through turbulent layers, and finally crosses space as a steady gift. For the system around it, the star is policy and weather. Its gravity gathers almost everything, holding more than 99 parts out of 100 by mass. Its gravity gathers virtually everything, so planets and small bodies curve around it without protest. Its light and wind write the rules for temperature, chemistry, and erosion on every air and rock. On worlds with stout magnetic fields, incoming particles are bent aside. On worlds with weak fields or none, the wind can gnaw at the upper atmosphere, molecule by molecule, especially where lightest gases are concerned. Over eons, those small leaks add up, and surface conditions drift. Yet, there is patience in all of it. The changes that reshape a climate or revise a sky often take far longer than our brief measures of time. And the star's constancy provides the backdrop against which those slower transformations play out. Every so often, a large outburst reminds the system that the calm carries power. Coronal mass ejections peel away from the sun's atmosphere and race outward, and if their embedded magnetic field points just the right way when it meets ours, the coupling is strong, currents are driven, and auroras brighten while high-frequency radio grows quiet. Most pass by harmlessly, the energy dispersed across a bubble too large to grasp. Planets farther out feel less from each storm, the gusts stretched thin by the size of space, yet they still register subtle changes in their own magnetospheres. The bell is rung at the center, and the tone fades as it spreads. None of this needs tending. The machinery runs because gravity, pressure, and quantum rules make fusion natural at the necessary densities and temperatures. Convection occurs because hot material rises and cooler material sinks. Magnetic fields arise because moving, conducting fluids generate them, and those fields store energy that is later returned to heat and motion. The outward rush of light and particles ceaselessly pushes against the thin haze between stars, and that boundary swells or shrinks as the pressure outside changes on scales much larger than the system itself. In the midst of this, the star's output leans toward balance, enough to keep a temperate world suitable for oceans and air, enough to keep far giants in weather of their own. If you are listening with eyes that grow heavy, you do not need to hold numbers. It is enough to know that a central engine burns quietly, that its surface trembles with small signals we can read, and that its breath carries a magnetic spiral through the family of worlds. You can let the rest soften. The star keeps its watch without you. The current turns quietly, and we drift to the innermost shore. As the tide shifts, we drift there next, and the details remain gentle in your hands. Closest to the star, a compact world traces an elongated loop and endures stark contrasts between day and night. Under the high sun, surface temperatures rise enough to soften metal. After sunset, with almost no air to trap heat, the warmth escapes into space, and the ground plunges to deep cold. There is no thick blanket of gas to share heat from bright side to dark side. Instead, Mercury wears a delicate exosphere, a near vacuum filled with atoms knocked free from rocks by sunlight, micrometeoroid strikes, and sputtering from the solar wind. Sodium and potassium can be detected by their glow. Oxygen and other fragments appear in the faint halo that hugs the surface. These atoms rarely meet one another. They follow arcs, bounce off the ground, and drift away, replenished as quickly as they are lost. Inside, the planet is mostly metal. An iron-rich core takes up an unusually large fraction of the radius, compared with other rocky worlds. A clue to a past shaped by intense early processes. Perhaps lighter silicates were stripped in a giant collision, or perhaps the inner disk near the young star favored heavy elements, as high temperatures discouraged the assembly of lighter materials. Whatever the path, the result is a small globe with a large heart. Part of that core remains liquid, and motion there generates a modest magnetic field. The field is weak compared with Earth's, yet it still sculpts the flow of charged particles around the planet, compressing the magnetic bubble where daylight strikes and drawing out a long tail on the night side. When gusts from the sun strengthen, Currents intensify in the tiny magnetosphere, and particles rain down in places where field lines guide them to the surface. The crust carries marks of great age. An impact basin known for its broad size shows a ringed floor and a surrounding patchwork of fractured planes. Elsewhere, wrinkled ridges lobate scarps cross the landscape where the entire planet shrank slightly as the price. Interior cooled and contracted, pushing pieces of crust over one another. Smooth plains fill older depressions, likely laid down by volcanic eruptions in the distant past, when heat inside was more easily released through fractures. More recently, strange bright hollows appear where volatile rich rock has been lost to space, leaving shallow pits with fresh-looking edges. Each of these features is a sentence in a long story: heat fading, rock shifting, and impacts recording the traffic of a busy early system. Near the poles, where the sun hangs low and casts long shadows, some crater floors never see daylight. Those permanently shaded places remain cold enough to preserve water ice delivered by comets or formed by chemistry at the surface. Radar reflections bounce back brightly from those regions, and thermal data agree that the temperatures stay low. A layer of darker material may blanket parts of the ice, helping trap the cold. It is a quiet paradox, close to the star, where the day side bakes. Hidden pockets store frozen water in darkness that has lasted longer than we can imagine. Geometry can be more decisive than distance when the light is shallow and the walls are high. Mercury's rotation holds to a rhythm that is neither simple day-night nor chaotic. The planet spins 3 times for every 2 circuits around the star, a resonance that locks the length of day and the position of perihelion into a repeating relationship. That pattern, shaped by tidal forces and the world's elongated orbit, means that the same longitudes receive noon near closest approach in one cycle and then again after another pair of orbits, giving some surface spots a unique history of heating. This resonance keeps days and nights long by our standards, and it gives observers a regular dance to track if they mark the sky with careful notes. Even the path around the sun whispers a deeper rule. The point of closest approach shifts forward slightly with each orbit, more than the pull of other planets can explain. The extra turn matches predictions from the curvature of space-time around the star, a small correction that realigns Mercury's ellipse over time. In that confirmation, a theory about gravity showed itself to be more than mathematics. It became a measured fact on a scorched and airless world. The planet's motion is not a perfect loop on a 2-dimensional page. It is a real path in curved geometry, and the small advance accumulates into a slow swirl of the perihelion through the ages. Missions that flew by and orbited have mapped the surface and weighed the interior. They found the core larger than expected, detected the magnetic field's off-center geometry, and read the elemental composition of plains and highlands. They traced subtle variations in gravity that reveal buried structure and imaged cliffs that cut for hundreds of kilometers. They watched sodium glow in the exosphere and saw how it brightened and dimmed when the solar wind changed. They measured the thermal breath of the ground as it warmed and cooled across a long day. Each instrument translated a different aspect of the planet into a language we can keep, making the unfamiliar immediate without raising the voice. Daily life finds reflection in such extremes. Where heat builds quickly, shade matters. Where coolness returns with speed, storage is precious. Where there is no air to carry sound, only direct contact can transmit a tap. You can let that thought soften your own evening. Warmth that lingers if held, calm that returns when you let a thought go. Mercury teaches that even without a thick cover, cycles can be regular and long. Heat blurs, and the view turns to a globe veiled in thick light. Venus waits one step outward, a twin in size that chose a different story. The air is thick with carbon dioxide, and clouds hold droplets of sulfuric acid that drift in layers like pale curtains. At the surface, pressure presses as if hundreds of meters under an earthly sea, and temperatures settle well above any kitchen flame. Heat does not escape easily. It is trapped and recirculated, so that day or night matters less than altitude and chemistry. The ground stays hidden under permanent overcast, and light that filters through is muted, filtered, and strangely even. The world turns slowly, almost reluctantly, and it turns the other way, so that the sun would rise in the west and drift toward the east over a very long day. That slow spin changes how winds organize and how energy flows through the atmosphere from high to low. At the cloud tops, air races around the planet in a few Earth days. This fast super-rotation is a product of solar heating, planetary waves, and the way friction and stability vary with height. Below, in deeper layers, the motion slackens. The atmosphere carries most of the heat rather than the rocks beneath. So weather lives in broad, slow currents and delicate cloud textures rather than in sharp fronts and rainstorms like our own. Sulfur dioxide and water vapor exchange between cloud decks and lower levels, making patterns that shift with illumination and with the breaking and recombining of molecules under harsh ultraviolet light. Lightning may flicker inside deep clouds, the charges built by turbulence and the collisions of particles in thick, stratified air. From orbit, the clouds trace long ribbons and polar vortices that resemble enormous, steady whirlpools, each anchored by rotation and temperature contrasts. Venus's rotation period is longer than its year, and that geometry shapes the budget of sunlight across months. Days stretch into months, nights do the same, and the imbalance between incoming and outgoing heat is managed by the scepter, great envelope of gas. Without a strong global magnetic field to deflect charged particles, the upper layers of this envelope meet the solar wind more directly. An induced magnetosphere forms as the ionized atmosphere interacts with the wind, draping field lines around the planet. At the high edge of the air, atoms can be stripped away, and lighter components escape across ages, a gradual thinning at heights where gravity's grip is weakest. The lower air remains dense and heavy, anchored near the ground by its own weight, hardly touched by those distant negotiations with space. The crust beneath is shaped by volcanism and deformation, rather than by planet-wide plate motions. Broad-shield volcanoes spread flows over wide areas, building up plains and gentle slopes. Features called tesserae, marked by complex patterns of intersecting ridges and troughs, rise like tough, ancient blocks that endured compressions and stretches across different eras. Rifts and chasmata cut through plains, testifying to crustal extension and the movement of material below. Some regions show patterns that imply more recent activity. Fresh-looking lava surfaces, thermal anomalies, and the distribution of gases that change with time. The record hints that resurfacing may occur in episodes, long, quiet stretches, punctuated by widespread activity, rather than as continuous rearrangement. The heat engine inside is slower than Earth's in some ways, faster in others, and the absence of ocean water to lubricate and weather the crust alters the outcomes profoundly. At altitudes well above the oppressive ground, conditions soften. There are layers where air pressure approaches values humans know, though the chemistry remains corrosive and the temperature still warm. In those heights, winds stream and waves ripple through the cloud decks, carrying information from day to night and pole to pole. Droplets grow and evaporate, seeds for streaks that mark levels like tree rings in motion. Sunlight at TIN, ultraviolet wavelengths, paints the clouds differently from visible light, revealing regions that absorb more or less and may be tied to unknown trace compounds. The atmosphere is not a simple blanket. It is a system that sorts and mixes, that builds structures in shear and then lets them fade. Venus offers a comparative lesson. Here is a world with near-Earth gravity, a familiar size, and likely stores of rock and metal arranged in a differentiated interior, but with an outcome that diverged. Dense air holds heat in, radiating to space efficiently, only at high, cold levels where the greenhouse gases finally release their energy. The slow rotation weakens Coriolis forces and favors broad cells over narrow, intense storms. Without surface water and with a sky that acts as a shield, weathering works differently, and the crust retains heat in patterns unknown on our ocean world. When we study this planet, we learn not just about the conditions that prevent liquid water at the surface, but about the range of ways a rocky globe manages energy. The warning is quiet, not alarmed. Change the balance enough, and the final state can be steady but inhospitable. The emotional anchor here is patience under weight. Imagine an atmosphere so heavy that each step would feel like walking through folded quilts of air, and each sound would travel sluggishly. Yet the system finds its own order. Fast winds where the air is thin, slow motions near the ground, chemistry adapting to light and darkness without stopping. You can take from that a softness for your own evening pressure can be real, and still there can be structure that carries you through it. The cloud deck parts, and a blue sphere steps into quiet focus. As the current mellows, we cross to that steadier ground without hurry. Here, water runs the script with rock and air as constant companions. Oceans cover most of the surface, storing heat and releasing it, moving salt and carbon around the globe in currents that respond to wind, rotation, and density. Sea ice grows and shrinks with seasons, changing how sunlight reflects and how heat escapes to the sky. Above the water, air rises where it is warm and sinks where it is cool, creating cells of circulation that carry moisture from oceans over land and return it as rain or snow. Clouds reflect light by day and trap heat by night. They form where air lifts and cools, and evaporate where air sinks and dries. The hydrologic cycle turns continuously: evaporation, condensation, precipitation, runoff, and return. Each step powered by energy from the sun and balanced by the planet's rotation and topography. Beneath that moving skin, the crust rides on a ductile mantle. Plates separate at mid-ocean ridges, where magma emerges and cools into new seafloor. They meet at trenches, where cold, dense lithosphere sinks, carrying water and minerals into depths where new melts are born. Along some edges, plates slide past, storing stress, releasing it in earthquakes that shift landscapes by meters in seconds. On continents, collisions lift mountain ranges that weather grain by grain, sending sediment down rivers to basins where it piles, compacts, and turns to rock. Over millions of years, volcanoes return carbon to the air, weathering draws it down, and the long partnership keeps surface temperatures within ranges that allow liquid water to persist. It is not an exact balance at every moment, but the feedbacks are strong enough to resist runaway tendencies, and life itself participates by altering chemistry and albedo. Inside, a metallic outer core spins and stirs. Convection there generates a magnetic field that reaches far into space, shaping a cavity in the solar wind. The magnetosphere deflects many charged particles, funnels others along field lines toward polar skies, and lowers the rate at which light gases escape. In the upper atmosphere, ultraviolet and X-ray light split molecules and heat rarefied layers, creating ionized regions that reflect some radio waves and glow in faint airglow at night. The field is not fixed. It wanders, strengthens, weakens, and has reversed polarity many times in the rock record. Yet across human history, it has been present. a silent defense that lets the lower air remain thick and moist. The moon's pull lifts oceans twice a day in most places, the bulges chasing the line between Earth and its companion while continents interrupt and amplify. Tides mix coastal seas, shape estuaries, and move sediment. The energy lost to tides slows Earth's rotation slightly and sends the moon creeping outward centimeter by centimeter each year. The satellite's size relative to the planet is unusual among rocky worlds and dampens wild swings in Earth's tilt. That steadiness keeps seasons within a range where ecosystems can adjust. The moon also preserves an archive on its surface, impact scars and volcanic plains unchanged by weather or plate recycling. A chronicle we can read to date events across the inner system. Life covers and fills the planet, altering the sky and the ground. Plants and microbes draw carbon dioxide from the air and release oxygen. Soils store carbon and nutrients that feed roots and streams. Some organisms fix nitrogen from the air, making it available for others. Some precipitate shells that later become limestone, a reservoir that locks carbon in stone. Over deep time, these processes have cooled the planet during high CO2 eras and warmed it by releasing buried carbon during others. The living layer is thin, but its effects are large, and its sensitivity to climate links it back to the circulation of air and water. Even at night, when photosynthesis rests, respiration and decomposition continue, part of a cycle that moves atoms through bodies and back to air or sea. From orbit, the planet changes color and texture with season. Snow advances and retreats, forests brighten, deserts shift subtly, and phytoplankton bloom in spirals where currents stir nutrients to the light. Storm tracks arc across oceans, then sweep rain inland, where rivers rise and fall according to basin and season. Over mountains, standing waves sculpt clouds into ripples. Over warm seas, cyclones grow if wind shear and temperature support them. The variety is orderly. Rules of fluid motion, heat, and phase change draw familiar patterns in new places each day. Calendars and climate normals let us expect certain rhythms, but every year finds its own version of the script. The emotional anchor here is companionship. This world hosts oceans that balance heat, rocks that travel and return, and an atmosphere that shelters and breathes in time with sunlight. It leaves room for sleep, even while it moves. When you lie down, tides keep timing, winds keep shaping clouds, and the ground holds still enough to trust. If you listen closely to your own breath, you find a small analog to the larger cycles, in, out, and the pause between. Colors cool to rust, and slopes lengthen under a thinner sky. As the thought continues, we cross the narrow space to that colder air. The red planet keeps a thin coat of gas that does little to hold heat when night returns. Carbon dioxide makes up most of that air, with nitrogen and argon joining in smaller amounts. Pressure near the ground is less than 1/100th of sea level on Earth, enough to raise dust and carve dunes, but too little to support liquid water for long at the surface today. Temperatures vary widely with latitude and time, dropping well below freezing on most nights. In the afternoon of local summer, rocks warm and release heat back to the air. After sunset, warmth leaks quickly to space, and frost can bloom where humidity and cold meet quietly at dawn. Dust plays a central role. The particles are fine, sometimes only micrometers across, and their colors redden the sky and soften shadows. Under the right conditions, local whirlwinds lift spirals that sweep dark trails across lighter ground. Under rarer alignments of season, temperature, contrast, and wind, storms can expand until they wrap the globe and last for weeks. These events reduce sunlight at the ground, cool the surface in daylight, and warm the air at altitude by absorbing infrared radiation, shifting circulation patterns until the storm spends itself. Between such episodes, calm dominates, and thin clouds of water ice drift over volcanoes or collect along fronts where air rises. Mars carries scars from a time when internal heat drove more vigorous activity. A great swell in the Western Hemisphere hosts shield volcanoes that dwarf anything on Earth, built by lavas that erupted repeatedly from hotspots anchored below a crust that did not march on plates. Among them, towering summits rise with slopes so gentle that a casual walker would not feel climbing until distance told the truth. On the other side of the planet, a canyon system stretches for thousands of kilometers, with walls that step down in layers and side canyons that braid. The landscape records extension, collapse, faulting, and scraping by landslides that ran for astonishing lengths under low gravity. Impact basins and craters of many sizes count ages like tree rings. Where craters are sparse, surfaces are young. Where they are dense, surfaces have stood long against weathering. Water once moved more freely here. Valley networks branch like rivers on Earth, and deltas lie frozen where channels met ancient lakes. Minerals that form in water, phyllosilicates, sulfates, carbonates, appear in maps as signatures of different eras and environments. Neutral waters that built clays, acidic waters that crystallized sulfates, transient brines that left salts. In the polar regions, layered deposits of carbon dioxide and water ice grow and shrink with seasons and longer cycles, recording changes in sunlight and climate. In the mid-latitudes, radar reveals buried ice under blankets of dust and rock, preserved where temperature and pressure allow stability. This ice is a store of the past and a clue to the future, should warmer times or geological heat bring melt to depths. Today's magnetic environment is a patchwork. The planet does not sustain a global dynamo now. The outer core may have cooled or convected differently, and the field faded. But crustal rocks in ancient terrains hold remnant magnetization, fossil fields that point to a time when a shield stood high above the atmosphere. Where these patches linger, charged particles are guided in unexpected ways, and the upper air meets the solar wind with local quirks. Without a global shield, light gases escape more easily, especially when the sun is active and the wind presses harder. The atmosphere thins grain by grain, balanced partly by volcanic outgassing in the remote past, and by modern releases that are small by comparison. Seasons arise from an axial tilt similar to Earth's, so light and temperature shift with latitude and time of year. The year lasts nearly twice as long, so spring and summer linger, and the atmosphere breathes with carbon dioxide that freezes onto one pole in winter and sublimates back in spring. Pressure at the surface rises and falls as that exchange proceeds, nudging winds and dust lifting in rhythms that repeat each Martian year. The orbit is slightly more elongated than Earth's, so southern summers are warmer and shorter than northern ones, an asymmetry that influences storm likelihood and polar patterns. Rovers and landers have made the unfamiliar concrete. Wheels have traced tracks across basaltic sands and over slabs of sediment that crack in polygons as they dry. Drills have sampled veins of calcium sulfate, where water once moved through rock. Spectrometers have read organics, bound in minerals, and measured methane in faint, variable hints that raise questions about sources in rock or atmosphere. Small helicopters have risen in thin air to scout routes, their rotors spinning far faster than earthly machines to lift in a rarefied sky. Orbiters map minerals, ice, and dust from above and act as relays for voices at the ground. Science there unfolds like careful walking. Small steps, long attention, data gathered under a sky that reaches a pink twilight even at midday when dust is high. The emotional anchor here is resilience without rush. This is a place where change takes its time. Volcanoes built in repeated outpourings, canyons opened through long failure of support, and ice stored in shade for ages. The air is thin, but motion persists. The cold is deep, but sunlight still paints slopes and wakes winds by noon. You can carry that steadiness into your own breathing. A gentle rise, a gentle fall, and a pause long enough to notice you are safe. Another lantern appears farther on, its glow steady and banded, with storms that last longer than countries, and a field that wraps a captive sky. As the night goes on, we will reach it, and wherever your eyes are now, they may close. Between the orbits of Mars and Jupiter lies a broad neighborhood where distance is the rule and collisions are rare. The asteroid belt holds millions of bodies, yet space between typical neighbors is so generous that a spacecraft may cruise for weeks without passing close to anything at all. The belt did not assemble into a full-sized planet. Early in the system's youth, resonances with the nearby giant tugged repeatedly on growing embryos and stirred the region until mergers were discouraged and fragments remained. What survived are pieces that record the heat, impacts, and chemistry of a time when the planets were still writing their first lines. Their orbits are mostly stable, gently tilted and mildly elongated, a library ordered by gravity rather than shelves. Much of the total mass is concentrated in a few large residents. Ceres, nearly 1,000 kilometers across, is round under its own weight and belongs to the small class of dwarf planets. Its density tells of rock mixed with water-bearing materials, and its gravity field suggests internal layering, a rocky core under a shell laced with hydrated salts and remnants of brine. Bright areas on a broad crater floor turned out to be sodium carbonate and related deposits, left when salty fluids reached the surface and then froze and sublimated, concentrating crystallized residues. This is cold volcanism by another name, chemistry driven by internal heat, low enough to preserve ice but high enough to move water and salts upward. Vesta, smaller but still massive, took a different path. Early heating melted it partway, separating metal toward the center, rock above it, and crust on top. A colossal impact opened its southern hemisphere, launching shards that journeyed for ages before some fell to Earth as a family of meteorites with the same crystalline signature. Two worlds, two outcomes, one region. The belt records both primitive and processed material within a few astronomical units. Many asteroids are not single stones, but loose gatherings bound by their own slight gravity. Radar images and visiting probes reveal boulder-strewn landscapes, low densities, and interiors that must hold voids like the spaces between pebbles in a jar. Over time, sunlight itself changes their spins. When a small body absorbs light and re-radiates heat, it emits a tiny push that can speed or slow rotation depending on shape and orientation. That subtle force, integrated across years, is enough to alter a day length or even reshape a rubble pile. Some objects spin so quickly that equatorial ridges form, material creeping outward until balance is restored. Others shed pebbles gently into space, adrift that can seed narrow rings or clouds near the parent body. Binary systems are common. In one arrangement, a small companion circles a larger primary in a dance that can be clocked from Earth by watching how their brightness flickers as they eclipse. In another, two similar partners orbit around a shared center with no clear leader. These pairs likely formed after impacts spun remnants past stability, or after gentle tides raised by the sun traded spin for separation. Even at a few kilometers across, gravity can stitch a relationship that lasts for eons if perturbations remain small. Their paths around each other are slow enough to be counted by a patient observer, yet steady enough to continue long after that observer sleeps. Composition varies widely because the belt samples different birthplaces and histories. Some bodies are rich in iron and nickel, remnants of shattered, differentiated parents whose cores were bared by violent strikes. Others are stony, with silicate minerals and little carbon, a record of moderate heating and modest alteration. The darkest class carbonaceous objects carry organics and clays formed when water percolated through porous rock in the heat of short-lived radioactive elements. When fragments from these classes arrive as meteorites, they carry hydrated minerals, amino acid precursors, and isotopic fingerprints of early solar chemistry. Each specimen is a page torn from a formation zone, a direct sample of a process we otherwise infer from light, reflected at a distance. Surfaces tell time by color and brightness. Micrometeoroid impacts and solar wind ions batter grains and change their optical properties, a slow space weathering that darkens and reddens many asteroids. Fresh material exposed by landslides or small impacts often appears brighter and less reddened until weathering begins its work again. Thermal inertia measurements reveal regolith texture. Coarse, blocky fields retain heat after sunset. Fine dust cools quickly and reheats at dawn. A body's gravity, spin, and collisional history set the balance between pebbles, gravel, and powder. Those differences matter when a probe samples the surface. A touch-and-go arm that expects sand may meet a bed of walnuts, and the hardware must yield gently to collect what it needs without bouncing away. Resonances sweep lanes through the belt, where objects are gently nudged over and over until their orbits change. Some of these resonant paths feed near-Earth populations, bodies whose elongated loops cross our planet's track and require cataloging and monitoring. The flow is small compared with the belt's size, but across millions of years, it populates inner neighborhoods with visitors that sometimes become meteors we can watch as fire, and more rarely, meteoroids that reach the ground as stones we can hold. Most find us as dust that glows briefly and vanishes, a quiet rain that adds grams across the globe each day. Our atmosphere's thickness and speed of arrival decide whether a piece survives or becomes light alone. Ceres and Vesta are not the belt's only markers. Pallas follows a path tilted steeply from the main plane, a reminder that the early system was restless and trespasses were common. Hygeia sits near the threshold, where gravity rounds a body into a sphere, a fragile boundary crossed by few. Families of fragments share similar orbits and spectra, children of a single shattering that left a parent misshapen and distributed siblings along neighboring tracks. Those clans disperse slowly as sunlight's small forces and gravitational taps separate them like smoke drifting in still air. A patient map shows strings that were once knots, time made visible by motion you can barely feel. The belt's emptiness is its defining calm. Images that crowd rocks shoulder to shoulder are stories for movies, not records of reality. In truth, orbits are clean, and meetings are rare enough to make headlines. That spaciousness preserves memory. Structures that would erode quickly in an atmosphere hold their edges for ages. Impact craters keep their rays until another strike paints new ones over the old. The lack of weather is a kind of weather. Nothing is smoothed by rain, rounded by rivers, or masked by snow that melts and moves. In that stillness, the belt holds its past, the way a quiet archive stores, letters dry, orderly, and waiting for careful hands. If you want one gentle tie to carry into your breathing, let it be the balance between distance and connection. Each stone keeps respectful space, yet all are bound by the same well of the sun's gravity and by punctuations from the giant that sits beyond. The neighborhood is not crowded, but it is communal. The rules are simple and patient. Orbits that repeat, spins that drift, chemistry that waits to be read. Another lantern appears ahead, larger than all others, and wrapped in bands that never sleep. As the current softens, we cross toward that giant disk, letting the belt's quiet fade behind us like footsteps absorbed by a wide hallway. Jupiter holds court with mass that exceeds that of all the other planets combined, and it turns quickly, completing a rotation in less than half an Earth day. That rush stretches clouds into parallel bands, bright zones and dark belts that wrap the globe from west to east. Inside those lanes, winds run fast and steady, hundreds of kilometers per hour in opposite directions on neighboring stripes. Along their boundaries, shear breeds waves, and where waves roll, vortices spin up and persist. One oval in the southern hemisphere has endured for centuries, shrinking and shifting color over decades but holding to its latitude with stubborn grace. Lightning flashes within deeper clouds betray tall convective towers where water condenses and releases heat. The same physics that powers thunderstorms on Earth, set inside a much larger engine. Jupiter radiates more energy than sunlight alone can explain. A slow contraction from formation stores heat, and helium may separate from hydrogen deep inside, raining inward and releasing gravitational energy as droplets fall. That inner warmth powers convection and feeds the belts and zones that circle the planet. Deeper still, the pressure is high enough to squeeze hydrogen into a metallic fluid that conducts electricity. Motion within this layer, guided by rapid rotation, generates a magnetic field so strong that it carves an immense cavity in the solar wind. The magnetosphere dwarfs the planet itself, stretches into a long tail, and traps charged particles in belts that can damage electronics and darken detectors in moments if a spacecraft strays or lingers without care. Auroras glow above the poles as that trapped energy precipitates along field lines into the upper atmosphere. They are not shy. Ultraviolet and infrared emissions form rings and spots that brighten and fade as the solar wind changes, and as the planet's own volcanic moon injects new material into the environment. That moon's eruptions feed a torus of ions along Godid, its orbit, a reservoir that loads the magnetosphere and thickens the radiation belts. The field also couples to the deep interior and to the ionosphere, driving currents that can spin the upper atmosphere slightly faster than the clouds below. The system is electrodynamic as well as meteorological, a coupling between plasma and wind that works in 3 dimensions and across many scales. The cloud deck is layered. Ammonia condenses highest, forming pale tops that hide deeper levels. Below, ammonium hydrosulfide may form under certain pressures and temperatures, and lower still, water condenses into clouds that drive the strongest lightning. Color comes from trace compounds modified by sunlight and by energetic particles, products of chemistry that stains the tops and gives belts their browns and reds. Eddies organize into strings, ovals merge or graze each other and then move on. Plumes erupt along jet cores and fade into sheared blankets. From a distance, the disk can look serene, but there is no true stillness. Patterns endure by renewing themselves from below. Rings surround the planet, but they are faint, dusty arcs maintained by impacts that knock grains from small inner moons. Backlit by the sun, these rings show as delicate curves that hug the equator, a reminder that even here, near a world of storms and radiation, collisions grind material, and light pressure sweeps it into structures that persist. The large moons beyond the rings lock into resonances that keep their orbits rhythmic, and those rhythms pump tidal energy into interiors where ice and rock flex. The planet is not alone. It sits at the center of a miniature system whose members tug on one another in ways you can calculate and then confirm with telescopes and probes. Gravity harmonics, measured by passing spacecraft, probe the interior. The data suggest that heavy elements may be diluted into the deep layers rather than confined to a sharp-edged core. That distribution, if real, points to complex formation and mixing, perhaps impacts by large embryos, perhaps slow erosion of a core into overlying metallic hydrogen, perhaps both. Differential rotation likely extends far below the visible clouds, with zonal flows that penetrate to depths where pressure begins to change hydrogen's behavior. The planet's shape, slightly squashed at the poles by rapid spin, reflects these interior motions and the sharing of mass between levels. Jupiter's weather is an archive of fluid dynamics at planetary scale. Jet streams arise from conservation laws and from the way rotation sorts flow into bands. Baroclinic instabilities develop, where temperature gradients and wind shear meet. Vortices shed, combine, or decay depending on the energy available and on the background flow that carries them. The planet provides a view of these processes with clarity we cannot achieve on Earth, free from topography and with a longevity that allows patterns to be followed across years. It is a laboratory in the open, audible to cameras that see in many wavelengths and to instruments that count lightning strokes hidden below the topmost haze. If you want a tie to your own evening, let it be steadiness within motion. The belts run, the ovals turn, and the jets shear, yet the whole obeys simple rules that endure. The giant's rotation is fast, but its changes are slow enough to watch, and even the oldest storm modifies itself gently, rather than breaking apart in a single hour. That calm persistence is easy to carry into breath. Points beside the giant resolve into 4 distinct shores. 4 companions circle the giant, each one carrying a separate history, each one answering the same tides in a different way. The innermost is Io, a world heated by constant flexing as it rushes around Jupiter and trades small tugs with its neighbors. That flexing converts orbital energy into interior warmth, and the result is relentless volcanism over a rocky mantle. Plumes rise hundreds of kilometers above vents and fall back as sulfur and silicate frost, staining plains in yellow, orange, and black. Fresh deposits hide old impact craters, so the surface stays geologically young compared with most moons. Lava lakes overturn, crust breaks into rafts, and shorelines shift as heat rearranges the crust from below. Gases released into space become ions along Io's path. They form a torus, encircling the planet, feeding the magnetosphere with material that glows under ultraviolet light. That exchange is continuous. Eruption, escape, ionization, and return as charged particles, moving along field lines toward auroras at the poles of the primary. The next orbit outward hosts Europa, smaller than Earth's moon, and covered by ice that looks broken and refrozen. Linear fractures, double ridges, and chaos terrains spread like scars where blocks drifted, rotated, and settled again. Evidence for a global ocean beneath comes from multiple directions. Induced magnetic signatures consistent with a conductive layer, densities that imply water and rock segregation, and surface chemistry that includes salts likely lifted from below. Tidal heating supplies the energy to keep water liquid at depth, and slow convection in the ice shell may move heat upward in cells. Where ice thins, it can open to briny slurries that freeze and lift ridges from beneath, explaining the paired rails that crisscross the face. The ocean itself is a candidate for habitability because it contacts rock at the seafloor, where water and minerals can trade energy in hydrothermal reactions. Oxidants made at the surface by sunlight and radiation might trickle downward through fractures, creating a chemical gradient that is valuable for metabolism. Thickness of the shell varies in models from single-digit kilometers to many tens, but all versions support slow movement and intermittent openings, a quiet restlessness that writes lines across bright plains. Ganymede, larger than Mercury, holds rock and ice in layers and adds a distinction unique among moons, an intrinsic magnetic field generated within. That field interacts with Jupiter's field to create shimmering ovals of aurora in a thin atmosphere, ovals that shift as the external field varies. On the surface, light grooved terrains cut across darker, older plains. The grooves are signs of tectonics that extended and faulted the crust, aligning ridges in broad swaths that run for hundreds of kilometers. Underneath, models propose an ocean arranged in multiple stacked layers, separated by different high-pressure phases of ice, a sequence made possible by the chemistry of water at varying pressures and temperatures. Gravity measurements and induced fields support the presence of liquid, and heat from radionuclides in the rocky portion can maintain the deeper layers over geologic time. Craters are fewer in some regions, more in others. Both populations help set ages for surfaces that changed at different rates in different eras. The magnetic uniqueness, the layered interior, and the varied terrains mark Ganymede as a world that has been active and that still hosts fluid at depth under an ice crust strong enough to hold ancient patterns. Farther still is Callisto, a record keeper with a surface that looks older because craters cover it densely from pole to pole. Bright rings around some impacts extend for hundreds of kilometers, their ejecta frozen in place because weather has no grip. Beneath that battered face, data hint at a conductive layer consistent with salty water. If an ocean exists here, it lives under a thick shell and does not drive large-scale resurfacing, so Callisto remains a contrast within the family. Internal heat is lower, tides weaker, and geology quieter, yet liquid may persist in the dark. The surface chemistry includes carbon dioxide frost, patches of bright ice, and darker mixtures thought to include organics altered by radiation, a thin veneer that speaks to space weathering and to the minor traffic of dust and small impacts. This is a place where change takes long spans and where memory is preserved rather than rewritten. The four together demonstrate how resonance sculpts diversity. Io, Europa, and Ganymede are locked in a ratio that repeats. For every orbit of the outermost participant in the chain, the middle completes 2, and the innermost completes 4. That pattern maintains a steady pump on eccentricities and keeps tidal heating alive. Energy allocated by gravity turns into heat within rock and ice. Heat changes surfaces and interiors. Changed surfaces feed back into the environment via gases, dust, and plasma. Even their thin atmospheres differ. Sulfur and sodium compounds hover around Io. Oxygen and water products trickle off Europa. Traces of oxygen and ozone gather above Ganymede. Carbon dioxide and other volatiles lie on Callisto's ground. Each moon's field, or lack of field, changes how particles strike and how sputtering lifts atoms into space. Seen from afar, the quartet is a procession of points. Up close, they are laboratories with different conditions, arranged by a single hierarchy of mass and distance. One erupts because friction needs it. One hides an ocean under a fractured shell. One carries a dynamo inside ice. One keeps ancient scars and hints at liquid beneath. This set reaches the feelings easily. One household, 4 personalities, each carrying a task that never ends. A listener can rest in that pattern-shared pull, separate outcomes, because it rhymes with families and with the way small differences in pressure or geometry near us become large differences over time, without echoing any earlier phrasing, except only this. Variety under one rule creates a calm pattern, and that pattern is comforting. As the story drifts forward, the next scene widens to a globe wrapped in pale rings, where ice grains and gravity trace lanes that stay remarkably thin, while circling a soft-hued sphere. The planet, girdled by rings, turns slowly enough for clouds to form gentle bands and quickly enough for jets to organize them. Its atmosphere is built from hydrogen and helium with trace compounds that color the upper haze in muted gold. In that sky, storms rise when convection pierces stable layers, sometimes large enough to circle a latitude and leave a bright wake that fades over months. Lightning has been recorded in great tempests that recur irregularly, each one an outburst in a long cycle where deep water and ammonia exchange heat and condensate. Temperature changes with height and chemistry sorts with pressure, producing stacked cloud decks that vary by latitude and season across a lengthy year. The poles host polar vortices with complex shapes, the northern capped by a hexagonal jet that holds its geometry as airspeeds shift around it. That six-sided current is a standing wave in a band of fluid, kept in place by shear and planetary rotation, remarkable for its persistence and for the precision of its edges. Beyond the atmosphere, a ring system spreads for hundreds of thousands of kilometers in radius, while remaining astonishingly flat and thin. The particles are mostly water ice, with some contamination by darker grains, ranging from dust to house-sized fragments. Mutual collisions occur at low speeds, trimming eccentricities and tilts until fragments settle into narrow planes. Resonances with moons carve gaps and sculpt edges, places where the orbital periods of ring particles match simple ratios with a moon's path become locations where repeated tugs pull material into waves and clearings. Shepherd satellites flank some narrow rings to maintain sharp boundaries, their tiny gravities corralling grains and pushing back against spreading that would otherwise blur features. When the rings are seen edge-on from our line of sight, they almost disappear, the thickness so slight that sunlight slips past with hardly a mark. Turn the angle, and backscattered, light brightens icy sheets until they look nearly solid, though they are granular swarms. Material does not stay forever. Small grains interact with the planet's magnetic field and the plasma environment, becoming charged and following field lines inward where they are lost. Ionized water products spiral down and fall into the atmosphere, a phenomenon sometimes called ring rain. Over long times, collisions grind larger fragments into smaller ones that are more easily removed by drag and by electromagnetic forces. The mass of the system and the measured rates of loss suggest that the rings may be relatively young on geological scales, or perhaps renewed episodically by breakup events. Spectra of water ice, with small additions of silicates and organics, show that surfaces are kept bright, likely by ongoing collisions that expose clean interiors of grains faster than space weathering can darken them. Deep inside the planet, helium may separate from hydrogen at pressures where the mixture becomes immiscible. Droplets form and fall, releasing heat that augments internal energy available for circulation. Gravity field measurements reveal departures from simple rotation, signatures of deep wind patterns that extend far below the visible clouds. Those winds help set the temperature structure and feed the bands that we see at the top. The planet's oblateness, slightly flattened at the poles by rotation, reflects how mass is shared between layers. Together, ring dynamics and atmospheric dynamics tell a consistent story, order emerging from repeated small interactions, form maintained by resonance and feedback over long spans. Moons fill the space beyond and within the rings. Small shepherds skate along ring edges, shaping them. Larger moons sit at distances where resonances line up, setting pattern speeds for waves and guarding gaps. Some moons likely accreted from ring material in the past, while others may predate the rings and act as agents that keep structure tidy. Tidal interactions among moons can migrate orbits, and lock pairs into rhythms that keep the whole arrangement from wandering. Each pairing or resonance is a rule written in gravity and confirmed by long observation. At the poles, auroras bring light to high latitudes, produced by currents that couple the magnetosphere to the atmosphere. The planet's field traps charged particles and channels them toward polar skies, where they collide with atmospheric molecules and emit photons in familiar colors at unfamiliar intensities. Those curtains wax and wane with solar wind conditions and with local plasma supplied by moons and rings. Magnetic footprints connect moons to auroral spots, showing where moving conductors cut through field lines and drive currents along paths that end in light. Even here, where ice grains orbit in thin sheets, electricity and gas cooperate to carve subtle structures and rhythm into the night. The emotional note for this world is balance. Countless collisions in the rings do not make a roar. They make a laminate so smooth that shadows glide across it in quiet bands. The atmosphere surges in long storms, then rests under gentle jets. The system holds together because resonance, drag, and shepherding all work at once, like many hands setting a table at the same speed. One can accept that and breathe more evenly. Small, regular actions accumulate into stable patterns. Without repeating earlier phrases, imagine only a field of bright snow that refuses to clump, arranged in lanes by invisible fences that never break. When that image dissolves, the scene narrows to two moons, whose stories are colder and more chemical. One wrapped in a deep orange sky with lakes of liquid hydrocarbons, the other fissured at a pole where vapor sprays into space. The path flows quietly into that pair. Among the companions of the ringed planet, Titan holds a thick atmosphere that presses more densely than Earth's, mostly nitrogen with methane and other hydrocarbons as crucial trace gases. At the surface, temperatures linger near 94 Kelvin, permitting methane and ethane to exist as liquids that gather in lakes and seas, especially near high latitudes. Channels pick their way from highlands to basins, and deltas show where flowing liquids meet standing ones. Clouds arise when sunlight warms layers and lifts vapor to altitudes where condensation begins. They drift, and rain falls in patches tied to season. The hydrologic cycle here uses methane in place of water, yet the logic is familiar. Evaporation from a reservoir, transport in winds, condensation into droplets, and return as precipitation that shapes ground. Radar images cut through the haze and reveal dunes stretching across equatorial regions. These dunes are built from organic particles, likely produced high in the atmosphere when sunlight breaks apart methane and nitrogen and allows complex molecules to assemble. Winds align the dunes into long, parallel ridges that march for hundreds of kilometers. Between ridges lie flats and small hills, where bedrock of water ice appears under coatings of organics. Near the poles, seas span hundreds of kilometers, with shorelines that shift subtly as seasons move. Some basins are connected by channels that fill and drain under periodic rains or long-term changes in humidity. Waves have been detected under certain winds, small in height, but confirmation that surface liquids respond to weather like any basic sea. Beneath the crust, evidence points to a global ocean of water mixed with ammonia or salts, a mixture that stays liquid at colder temperatures than pure water would. Gravity and rotation measurements show that the moon deforms under tides by an amount that supports the presence of a decoupling layer, and changes in rotation hint at a shell that slips slightly over a fluid interior. The conductivity of that ocean interacts with external fields in ways consistent with ions dissolved in the water, a subtle signal that complements mechanical clues. The interface between rock and water at depth is a venue where chemical energy can be released as minerals alter and equilibrate. a slow engine that may have run for much of the Moon's history. The atmosphere itself is a factory for complex chemistry. Ultraviolet light from the Sun and energetic particles from the magnetosphere drive reactions that build hydrocarbons and nitriles. These molecules clump into aerosols that descend, forming the orange haze that hides the surface in visible light. Some are soluble in liquid methane and ethane, changing the behavior of lakes by altering surface tension and evaporation rates. Some are insoluble and accumulate as sediments that can be transported by winds and flows. Photochemistry varies with altitude and latitude. Conditions at high levels differ from those near the ground, so products form in layers and then mix or separate as they fall. Over long spans, this rain of organics seeds the surface with material that records the balance between production in the sky and removal or burial on land and lake beds. Season drives change over a long year. The tilt of the Moon and its path around the planet and Sun cause sunlight to move north and south over Titan's poles slowly. Storms tend to cluster in favored times as one hemisphere warms and convection strengthens. Lake levels adjust as evaporation and rain trade control. Clouds arise in bands and then thin to nothing. Dunes creep by centimeters each year under gentle winds. Shorelines etch darker lines as liquids recede and then surge again with a different season. The rhythm is long enough that a patient watcher can mark arcs rather than days, and the patient suits the cold. Across the system, a smaller moon offers a different route to liquid, Enceladus, whose south pole features parallel fractures that vent water vapor and ice grains into space. These tiger stripe fissures are warm compared with surrounding ground, warmed by tidal flexing that concentrates energy in the crust near the pole. The grains ejected carry salts and silica nanograins that hint at interaction between water and rock at the seafloor under the ice. That chemistry implies hydrothermal activity, where hot fluids percolate through rock and gain dissolved materials before joining the ocean. Organic molecules, both simple and complex, have been detected within the plumes, carried upward from water that never sees sunlight. Some of the ejected material escapes to orbit and replenishes a diffuse ring around the planet, a steady trickle that links a subsurface ocean to a visible structure in space. The south polar terrain also shows evidence of self-regulation. As vapor escapes, it cools by expansion and deposits frost along vent walls, which can narrow and alter the flow. Tidal stresses change, with the Moon's position in its eccentric orbit, opening and closing fractures in a predictable sequence that modulates plume output. Heat, produced by flexing, rises through fractures and escapes, but the balance between loss and supply can keep vents active across years. The presence of liquid water, a heat source, and a path to the surface makes Enceladus an attractive place to sample for signs of life's chemistry without drilling. A fly-through at the right height and speed can collect grains directly, study them in flight, and return results from a plume that is both a geyser and a messenger. Together, Titan and Enceladus frame two versions of habitability in the outer system. One considers a surface where liquids move under an atmosphere thick enough to support clouds and rain, with chemistry rich in carbon and nitrogen feeding a long chain of reactions. The other looks inward to a dark ocean heated from below, where vents may provide gradients in temperature and chemistry that power metabolism. Both are far from the sun's warmth, yet both show that energy can be gathered and used even where light is weak. They invite a gentle reflection. Conditions need not match our home exactly for interesting chemistry to proceed. Variety and patience can assemble complexity under different roofs. Proposed missions sketch careful paths, drones or landers to drift over dunes or float on a lake, orbiters to map surface change across seasons, probes to sample plumes repeatedly and measure variability across orbits and years. Each plan treats time as a partner, not a rival. Data, gathered in small batches, again and again, can reveal cycles that are otherwise invisible. The feelings that match this approach are curiosity without urgency and hope without strain. You can mirror that in your own breathing. Slow in, slow out, and trust that a sequence of gentle returns leads to a clear picture in the end. When the thought settles, the view will widen again to include a sideways world with a long season and a deeper blue farther out, and then a more distant giant where winds run fastest under a dimmer Sunday. For now, let the idea of lakes under an orange sky and fountains over a polar plain be enough. They continue whether anyone watches or not, and that continuity is a soft pillow. Uranus moves through its long year with an orientation that feels almost improbable. The axis lies close to the plane of its orbit, so one polar cap leans into sunlight for many Earth years, while the opposite cap turns away to a long twilight. Seasons are not quick switches here, they are eras. The hemisphere that faces the sun warms gently and steadily. The other cools and waits. The dividing line between them slides slowly as the planet advances. Methane high in the air absorbs the red end of sunlight and sends back a blue-green tint, while hydrogen and helium make up most of the bulk with smaller amounts of other gases layered below. In most years, the disk looks quiet through small telescopes. But when equinox approaches and the day-night boundary runs across the equator, bands sharpen, compact storms appear, and polar hoods brighten or fade, a sign that sunlight and circulation are rebalancing in step. The weather engine here runs on a modest intake from the sun and on slow interior heat that still leaks outward. Winds organize along latitude lines, but the patterns are subtler than the robust belts of a larger neighbor. Cloud particles form where temperature and pressure invite condensation, building bright features that drift with jets and shear along edges. Infrared views show layers stacked by chemistry and by altitude, each reacting differently when the slant of light changes at the start and end of a long season. The response time of the atmosphere stretches across years. Nothing snaps. Adjustments ripple through the layers like a slow tide in deep water. Inside, conditions shift from a light outer envelope into high-pressure phases of water, ammonia, and methane that behave like conductive fluids under the weight above. Models place a compact, rocky center within that mantle, with temperatures high enough to keep those ices in ionic or supionic states. A magnetic field arises from motion in these conducting layers, but it does not align with the spin as neatly as Earth's does. The field is tilted by several tens of degrees and offset from the center, so the magnetosphere is lopsided and rotates a skewed pattern through space. Charged particles, guided by that geometry, precipitate in places that do not match simple geographic poles, and auroral emissions appear where the field meets the upper atmosphere on paths that vary with rotation and solar wind pressure. A ring system circles the planet as narrow, dark arcs discovered when a star briefly winked behind them. Compared with the bright sheets of another giant, these rings are dust-poor and built from larger fragments that reflect little light. Shepherd moons likely keep edges crisp and lanes narrow, exchanging small tugs that hold particles in place against the spreading that collisions would otherwise cause. Farther out, larger moons carry histories written in icy plains and darker patches where fragments from impacts drape the ground. Some surfaces show signs of flows that filled older basins. Some show networks of grooves where the crust extended and cracked. Their orbits settle into resonances that trade momentum gently, altering paths over spans longer than a human epoch, but shorter than the age of the system. A quiet reshaping that never hurries. The extreme axial tilt suggests a formative jolt, a substantial impact in the early era, or a sequence of smaller strikes could have toppled a growing world and left its interior layered in a way that displaced the dynamo and twisted the magnetic field. That same event would have reset rotation and altered how heat moves upward, creating an atmosphere that remembers the tilt with its slow seasons and subtle winds. Climate models built from these pieces predict that while the topmost layers swing with light and darkness, deeper levels remain insulated, so temperature gradients are not as ruthless as the long days and nights might imply. The system favors moderation at depth, even when the cap above spends decades in brightness or in dusk. Motion here can be tied gently to your own sense of time. Where you live, daylight changes over months. Here, illumination changes over decades. Where you measure weather in days, Uranus measures in years. That gradual pace turns the planet's year into a calm canvas for small changes you can trust. A cap that brightens, a band that clarifies, a solitary storm that rolls for a season and dissolves. If you need one short image, think of a globe that doesn't spin upright like a top, but rolls on its side along a track, sunlight stroking one end for a long while and then crossing to the other. You do not have to hold more than that. The important part is pattern, not detail. Tilt, slow response, quiet magnetism, rings kept narrow by guardians you cannot see. Even the way the planet interacts with the solar wind reflects its geometry. The skewed field rotates through a stream of charged particles and creates a magnetosphere that inflates and deflates depending on how the tilted axis presents itself. Currents trace complicated paths between the outer boundary and the ionosphere, and precipitating particles write ovals of light where field lines thread the atmosphere. Instruments count those particles and read the field's direction as the pattern turns, building a map in time because space is difficult to cross. Over long intervals, data accumulates and the picture sharpens. Not a perfect symmetry, but a system that keeps time in a tilted frame. If you look for a feeling to carry from this world, choose acceptance. A planet can be deeply different, rolled onto its side, strangely magnetized, quietly ringed, and still be orderly. Its seasons do not match yours. Its storms do not shout. Its field does not point where you expect. Yet everything still obeys gravity, pressure, and conduction. That steadiness is a gentle permission to rest from comparing and let things be as they are. Light thins to a darker blue, and winds gather speed even where sunlight is weak. As the thought turns, we drift outward, and the pace remains unforced. Neptune holds the last major post along the planetary path, a deep blue world that trades bright sunlight for interior energy and sends that energy into motion. The top air carries methane that pulls red light from the spectrum and leaves the color we see. A saturated tone that darkens where clouds thin and brightens where crystal hazes gather. Despite the weak warmth from the distant sun, measurements show winds racing along latitude bands at speeds unmatched elsewhere, a sign that the engine driving them draws from heat rising slowly from within. Convection in lower levels organizes jets. Jets shape storms. Storms drift, merge, and fade on schedules that run from weeks to seasons. When bright systems appear against the darker background, you can watch them travel and shear on images taken days apart, a reminder that this far shore is not still. The planet's interior likely mirrors its tilted cousin in broad outline. A hydrogen-helium shell above, an extended mantle of high-pressure water-ammonia-methane mixtures beneath, and a rocky core at the base. The dynamo that generates the magnetic field seems to operate in a shell rather than directly at the center, producing a field that is strongly tilted and displaced from the middle. That geometry drives a magnetosphere that rotates an offset pattern through space, so its interaction with the solar wind depends not only on the wind's strength and direction, but also on the planet's own orientation. Auroral emissions mark where charged particles follow field lines into the upper atmosphere, flickering in ultraviolet and infrared, where currents close the circuit between space and air. Gravity data and thermal measurements refine how density and temperature vary with depth and suggest how heavy elements are distributed through the mantle. Small corrections that keep models honest. Triton circles backward relative to the planet's spin, evidence that it was captured rather than borne in place. Bringing such a large body into a bound orbit required shedding orbital energy, a process that must have disturbed earlier satellites and reshaped the system. Triton itself shows terrains that are comparatively fresh. Few craters, plains marked by polygonal textures, and flows that must be made from volatile ices rather than silicate lava. Dark streaks radiate from spots near the South Polar region, where geyser-like plumes have vented. Those plumes can arise when sunlight penetrates a thin, translucent ice layer and warms a darker sheet below, building pressure that breaks through and carries dust overhead before it settles back downwind. The atmosphere above is thin and made mostly of nitrogen. It thickens and thins across its year as sunlight and distance change, allowing frost to migrate from region to region and repaint the ground lightly between eras. Smaller moons keep their own awkward paths, many with inclinations and eccentricities that reflect a past of scattering and recapture. Faint rings composed of dark grains circle the planet in arcs rather than in continuous bands, clumpy segments sustained by resonances with nearby moons that corral particles against spreading. When the viewing geometry is favorable and the planet is backlit, those arcs show as fragile threads that betray the presence of dust where the direct glare of the disk would otherwise hide it. The same gravity that throws moons into odd orbits keeps these structures intact. The rules are gentle but persistent, repeated over and over with each circuit until the pattern looks permanent. Neptune teaches that strong motion does not require bright input. The difference in energy between the deep interior and the cold top layers is enough to establish gradients that drive winds, and rotation sorts those winds into jets. Where a jet sharpens or wavers, a storm can spin up. Some storms form dark ovals that move and change edges like ink drops stirred into water, surrounded by brighter companion clouds that condense in rising air. Others appear as bright spots, where methane ice forms at heights where temperatures are low enough to sustain crystals. Over time, these features are replaced by new ones as background flow and vertical structure evolve. The map is dynamic, but not chaotic. It is a changing answer to the same forcing. At this distance, changes in the solar wind take longer to arrive and spread wider when they do. The magnetosphere swells and contracts according to that pressure and according to the planet's own rotation through its skewed field. When the conditions align, auroral features brighten and move. When they slacken, the lights dim. These cycles couple far space to an upper atmosphere, where chemistry and temperature adjust in step. Instruments tuned to different wavelengths record these responses and help unravel which part of the energy budget goes to heat, which to motion, and which to light. Each dataset extends a baseline, and baselines matter more here than anywhere else. Because seasons are long and features recur on timescales, we must meet with patience. If you seek a feeling to take from this frontier, choose confidence in quiet reserves. Here is a planet with weak sunlight and yet energetic weather. A magnetosphere shaped by an off-center dynamo and yet stable enough to write repeating signatures in light. A captured moon that brings its own activity and yet settles into a workable orbit. You might think of it in one brief image: flags on a ridge that seems sheltered, moving, because a steady wind from behind the hill keeps blowing. You cannot see the source. You can only see the motion, and the motion is enough to trust that energy is present. Without repeating any earlier transition, the thought now opens beyond the giants to a deep, cold district where small worlds keep long, careful paths and store chemistry from very early days. And still, the night carries us along, easy and slow. Beyond the last bright planet stretches a district of small, cold worlds that keep their distance with quiet discipline. The Kuiper Belt forms a broad disk around the Sun, a zone where icy bodies trace paths that stay mostly in one plane but differ in tilt and roundness enough to make a textured map. Some orbits are almost circular, as if these residents grew where they now live and avoided deep entanglements with the giants inside. Others sit in resonant patterns where their periods match simple ratios with Neptune's, a gravitational handshake that repeats every few circuits and locks them into stability. Still others rise above and below the main sheet on inclined tracks, evidence of older shuffling when the large planets drifted and traded momentum, pushing certain objects outward and up into long, calm loops. Each class holds its own archive. Near-circular members preserve the neighborhood's original pace. Resonant bodies remember how Neptune moved. High-inclination objects carry a signature of scattering that never quite faded. Pluto travels among the resonant set, synchronized so that it never comes too close to the giant that shepherds it. The surface is a patchwork of ices made from nitrogen, methane, and carbon monoxide, each one migrating under weak sunlight according to season and location. A vast plain of nitrogen forms cellular patterns that turn out to be convection. Warm ice rises slowly, cool ice sinks, and the cycle renews the surface in lanes and lobes that move over spans far longer than any human calendar. Mountains of water ice stand like bedrock because water here behaves as rock does on Earth, hard, strong, and slow to deform. A thin atmosphere of nitrogen thickens as frost sublimates near perihelion and thins as gases refreeze nearer aphelion, building layered hazes that scatter light into soft colors when the sun sits low. Density measurements and geology point to differentiation, rock in the middle, ice above, and possibly a buried ocean sustained by radiogenic heat and by insulating layers that keep warmth from escaping too quickly. The idea of liquid sealed under ice in such deep cold is not a contradiction. It is a reminder that pressure and composition define what is possible. Other dwarf planets bring their own variations. Eris keeps company with a small moon that helped fix its mass and confirmed that it rivals Pluto in size. Its high reflectivity suggests a surface refreshed by frost cycles that erase darker coatings and keep ices bright. Haumea spins quickly enough to stretch into an elongated shape, a consequence of angular momentum held for aeons, and it carries a ring and a family of fragments that likely formed when a large collision shaved material from its surface. Makemake shows methane ice and bright patches that contrast with darker terrains, a sign that sunlight and particle impacts modify the skin at different rates in different places. These bodies do not repeat one story. They sample a spread of spins, sizes, compositions, and thermal paths, and together they show how many ways a small world can settle in steady cold. The belt's small members preserve chemistry that dates back to the solar nebula, with fewer revisions than rocks closer to the sunday. Organics condense onto grains and later become part of larger bodies. Water ice locks gases in clathrates and releases them slowly when warmed. Silicate dust remains as a stiff framework within mixtures of frost and carbon-rich compounds. When a handful of these objects are nudged inward by slow gravitational trades or by cumulative tugs at resonances, they can become short-period comets. As they approach warmer regions, Sunlight frees gas and dust. Jets turn on where dark patches absorb heat, and a coma forms around a nucleus that remains small and solid within the glow. The tails that follow do not trail randomly. Dust arcs under gentle pressure from sunlight and orbital motion. And ionized gases align with the solar wind. So, structure reflects physics as much as it reflects composition. Each return to the inner system strips some material. Each retreat to the outer districts allows crusts to seal and chemistry to rest. Orbits in the Kuiper belt keep time with Neptune in more ways than one. Resonant classes, including the 2-for-3 rhythm that holds Pluto, populate stable niches where a small body can survive for billions of years without a close approach that would eject it. Objects in these niches avoid the giant. By arriving at certain longitudes when Neptune is elsewhere, the geometry repeats, so the safety repeats. Beyond those sanctuaries, scattered disk bodies carry more elongated paths that reach toward the distant dark and then sweep back inward, often with a tilt that marks an encounter long ago. Over deep time, slow interactions with the planets and with one another adjust these tracks by small amounts, and an already broad population spreads farther, like chalk smudged by a sleeve across a slate. The belt remains a disk, but the edges feather with history. The emotional tie here is spaciousness with memory. Distances stretch so wide that change is measured in quiet shifts rather than in leaps. Light is weak, but it works patiently, moving frost from shade to sun and back again over centuries, drawing thin atmospheres where conditions allow and then letting them collapse when the heat is gone. You can borrow that pace for your own breath. Every inhale is a gathering, every exhale is a return, and the interval between them is the calm where chemistry waits. If a single image helps, picture an archipelago of islands spaced too far to see each beach from the next, each with its own weather, but all in the same wide sea. The belt is like that, remote, varied, and coherent, without being crowded. Science advances here by reading small signals with care. A star dims for a heartbeat when a distant body passes in front. That occultation fixes size and can reveal an atmosphere that bends light at the last moment. Reflected spectra show which ices and organics share the surface, even when light is scarce. Thermal measurements at longer wavelengths tell how quickly a surface cools after local noon, and how rough or smooth grains must be to match the curve of heat. Each method adds one thread. Together, they weave a cloth that turns faint points into places with geology, weather, and time. Missions that cross the belt convert inference to detail, but the foundation remains the same. Soft clues repeated and checked until they hold. When the thought is ready to move, let it move gently. Beyond this broad disk lies a zone where the sun's binding is still real, but the light has little leverage, a kingdom of long-period travelers that return only after ages. Before we go that far, keep one lesson from these cold isles. Variety emerges when forces are steady and time is long. That is enough to lower the shoulders and let the jaw unclench. Now the horizon slowly enlarges, and the distances grow by orders you can feel only as hush. Far past the Kuiper belt, the solar family thins to a sphere of hypotheticals we infer from the slow comets that enter from all directions. The Oort cloud has not been photographed. It reveals itself through trajectories. Bodies arrive on orbits so elongated that their far points lie nearly a light year from the sun, and their approach vectors scatter across the sky rather than aligning with any single plane. The best explanation is a very distant reservoir stocked in the earliest era, when the giants were still gathering mass and hurling leftovers outward. Those leftovers did not escape entirely. The sun's gravity kept hold, but barely, and passing stars, or the gentle tide of the galaxy, nudged them into a sphericized distribution that waits in cold so deep that chemical motion is almost stopped. When a nudge sends one inward, the clock that measures its return runs long. The nucleus is a compact mixture of ices and dust, often dark from organic coatings cooked slowly by cosmic rays during ages in the deep. As the traveler nears warmth, surface patches heat unevenly. Gases sublimate through crusts where fractures allow. Jets push in directions that can alter spin, and the coma grows like a scarf around the small body. Sunlight scatters from dust into broad tails that curve because particles keep part of their orbital motion, even as pressure spreads them. Ionized gases align with the solar wind and glow in narrow, straight lines that always point away from the sun, a geometry defined by field and flow rather than by the comet's path. Modern instruments resolve color and polarization in these structures and read which molecules are escaping, each species tracing a temperature and a history of binding within the nucleus. The edge of the heliosphere lies far inside this reservoir. The solar wind expands until it meets the pressure of surrounding interstellar gas. There it slows, its field lines draping into new directions under the influence of the medium beyond. Spacecraft traveling outward have measured abrupt changes in the character of particles and in magnetic orientation that mark this boundary. Inside, the sun's outflow modulates cosmic rays and reduces their intensity. Outside, those energetic particles from the galaxy travel more freely. The shape of the boundary is not a perfect shell. It responds to external pressure and to the angle between the interstellar magnetic field and the wind that streams from our star. Over years, the size and profile breathe according to the sun's own cycle and to changes in the neighborhood through which it moves. That larger neighborhood is not empty. The solar system rides through a region shaped by ancient supernovae, a bubble of hot, thin gas within which denser clouds sit like slow eddies. The sun currently moves through one such cloud, and neutral atoms from that medium drift into the heliosphere, are ionized by sunlight or collisions, and join the outflow. Instruments that count those atoms and their products map inflow directions and speeds, refining how we understand the interaction between the bubble we inhabit and the sea beyond. Dust grains from interstellar space also enter, and are bent or filtered by magnetic fields. Their arrival reveals sizes and charge states that test models of grain evolution in the galaxy. These are delicate measures, small signals, long averages, but they are part of the same story. Boundaries that aren't walls but gradients, exchanges that are continuous rather than sudden. Even at these distances, gravity does not end. The sun still holds the cloud. The galaxy still tugs on the cloud and on us. Passing stars occasionally add tiny corrections that accumulate. Over many orbits around the galaxy's center, these influences change which distant bodies are barely bound and which are free to drift. A few are encouraged inward on paths we can witness. Most remain dark and still, perturbed in ways we cannot yet sense, reminders that structure can exist far beyond the reach of bright light. The feeling attached to this part of the map is humility. The known object count is small compared with the likely population, and the names we use are placeholders for ideas we keep refining. Long-duration missions carry our senses into this gradient and allow patience to work. Counters for charged particles click quietly for decades. Magnetometers record angles and strengths that vary over hours and over years. Dust detectors notice occasional taps from grains that cross the instrument face. None of these data sets is loud. Each becomes meaningful because it accumulates, and because models built on earlier measurements predict what should happen next. When a pattern matches, trust grows. When it does not, a correction is made, and the map adjusts. That is not just procedure. It is a style of attention that suits the outer dark. Simple instruments, steady clocks, and a willingness to accept that answers will arrive a little at a time. If you want one brief image to hold, choose a shoreline at dusk where two seas meet. You cannot draw a sharp line. You can only feel the temperature change and watch how small ripples from each side pass through one another without argument. The heliopause is like that. Inside, the sun's breath is warm enough to push back. Outside, the interstellar medium gives the pressure that shapes the bubble. The place where they share is not fixed. It moves when either partner changes mood. You can rest in that uncertainty. It is structured, not chaotic, and it keeps working whether anyone is watching or not. We have now crossed a long arc from the center's steady furnace to the faint perimeter where the galaxy's weather tastes the sun's. The rules have not changed. Gravity curves, paths, energy flows from hot to cold, and matter's phases respond to pressure and temperature. Only the balances shift, and with them, the forms. With that, the story turns homeward to end in quiet, not because the map is finished, but because night has reached a depth where rest becomes the best instrument. Breathe once more and let the edge recede. The orbits will keep their time without your help. The journey unwinds softly now, like a ribbon drawn through calm hands. We moved from a star that glows with fusion to worlds that roll and spin, to belts and rings, to seas hidden under ice, to a tilted giant and a deep blue wind, and finally to a frontier that is more gradient than gate. Each place kept its own rhythm. None asked you to hold everything at once. The same few laws guided them, and those laws were gentle in their certainty. Gravity gathered, light traveled, heat sought cooler ground, and material changed state when pressure and temperature allowed. With just those ideas, the map stayed readable, even when the names blurred and the numbers softened into rounded memory. What makes the neighborhood restful is its reliability. Orbits repeat with such patience that eclipses can be foreseen long after we are gone. Cycles in fields and winds return in season, even when that season lasts years instead of months. Thin atmospheres rise and thin again according to sunlight and geometry. Mantles convect where heat is available and rest where it is not. Rings keep their lanes because countless small collisions cancel excess motion, and because shepherds stand guard without speaking. Even at the far edge, where the sun's breath meets the interstellar breeze, the line moves in ways that instruments can learn and predict. There is comfort in processes that do not need our attention to continue. They were here before us. They will remain after our thoughts quiet. If details slipped past you, let them drift. The point was never to memorize every speed or tilt. It was to feel how a system can be both active and calm, both complex and orderly, both vast and intimate. A storm that lasts for years does not rush. A season that spans decades does not shout. An ocean sealed under ice does not advertise its presence, and yet holds its warmth. This mix of steadiness and movement is a good teacher for a tired mind. You can take from it a small practice. Notice your breath. Arrive. Notice it leave. And trust that another will follow without instruction. You are resting on a world that rotates with dependable grace, lit from afar, wrapped in a blanket of gases that keeps you warm and safe. The tides turn, the air flows, and the ground holds steady where you are. Far above, satellites pass on arcs that meet again. Farther still, planets keep appointments marked long ago. At the edge, a boundary flexes in response to distant pressure and then finds its balance. None of this asks for urgency. None of it requires effort from you tonight. The universe is spacious enough to hold your curiosity while you sleep, and patient enough to return it, unspilled, when you wake. Lay down the last loose thread. Let the names of places dissolve into a gentle sense of order. Imagine only a quiet room inside a very large house. and beyond its window a sky that keeps its time without needing to be watched. That is the feeling to carry into sleep. Dependable motion, soft light, and distances that do not demand crossing. Your pulse can slow to match that rhythm. Your thoughts can soften like frost meeting morning warmth. It is safe to close your eyes. Thank you for traveling so far tonight. The path will be here when you return, the same and also new, because patterns repeat and details change a little with each round. For now, give yourself wholly to rest. The orbits will not wander while you dream. The rings will not fall silent. They will whisper to each other in collisions too small to hear. The edge will not harden into a wall. It will stay ashore, breathing in and out with the sun's long weather. Let the night take over. Let the quiet finish the lesson. Good night.